Section 3.5, other strategies for integration. Good news. This is a very quick section. I'm only doing one very short video for this. So there's two different techniques that your book talks about. One is the use of integration tables. The other one is a computer algebra system, which we will not be using in this class. The closest thing to a computer algebra system that we use is Desmos, which I will just mention briefly, but we've pretty much already learned what we need to learn about using Desmos. So I'm going to concentrate on integration tables to do two examples to get you started on that. So first of all, in More, you are going to want to download the integration tables, which look like this. The integration tables are in groups. So starting here, we have integrals that are in this particular form. So what you want to be looking at is, first of all, there's a radical. Okay, we have a square root of a quantity a squared minus u squared. Now this looks just like our trigonometric substitution techniques, some of these, all right? And so a is some type of a constant, could any type of a number, and u represents a function. So in the square root of a squared minus u squared, you have some constant squared, like 9, minus some function squared, which could be just something as simple as x, or it could be something like 16 minus the sine squared of x, okay, where the function u is equal to the sine of x. All right? So all of the formulas on the table of integrals are in terms of a's and u's, where a's are constants and u's are some type of a function. So to use the tables, what you really want to do is look at your problem and then look to see which of these sets of forms most closely resembles it. So let's go back to the first problem. What we have is the integral dx over 9x cubed minus 5x squared. Well, at first you're going to go, that doesn't look like anything on the table. Well, first of all, what you have to realize is you have to put this in terms of a's and u's, all right, and b's. B is also a constant, a's, b's, u's. So your u is some function. Well, what we can do with this denominator, there's nothing to do in the numerator, of course, but in the denominator, we could factor out an x squared. So I'm kind of showing that down here. I'm showing the development of it. Okay, so I'm letting a be equal to -5, b being equal to 9, and my u is x. All right, so you take 9x cubed minus 5x squared, you factor out the x squared, and you have this. Then if we let x be equal to u, we end up with this. And then we have 9 is b and a is 5, so we end up with this. And so if u is x, then du is dx. So we can take out the dx and put in du. So all we're really doing is kind of like a u substitution to some respect. And so we converted this right here into du over u squared times an a plus bu. So the question is that one of the forms? And so we go back to the tables. And so I looked through this first set, and all of these involve radicals up until down here. And that doesn't look like anything that I'm looking for. None of these do, because they've all got, square roots in them. I don't have a square. I don't have any kind of a radical in any of my problems. So I'm going to go down to the next group. Well, same thing. Now it's the square root of u squared minus a squared. So none of these resemble what I'm looking for. Well, let's go to the next group. Here's forms involving a plus a bu. Well, isn't that kind of what I had? That's what I was, so maybe it's going to be in here somewhere. So I go through these very carefully and look. And so I get down to, aha, number 50, du over u squared plus a plus bu. There we have it. There's my form. Now, it's not always that easy to find the right form. Sometimes you have to do a little bit more algebraic playing around. But the hardest part of using tables is getting the form to fit. Getting your problem, your integral, to look like something on this table. I'll show you that in the next problem. Once you have that, you simply take, this is just like when we were doing reduction formulas. All right, you got a formula now. You just plug in your A, you plug in your B, you plug in your U, and boom, you have the integration done. And so, going back to section 3.5, I just plugged in, here's the formula that we were just looking at. Plug in the A, the B, and the X for U, and there you have it. So the integrating, there really is no integrating to do. You're just writing down a formula and plugging in the numbers. The key, as I've already said, is getting it to look like what you want it to look like. So let's take a look at the next one. This is a good example of one that's challenging. So don't look at what I've done yet. Just take a look at this. And you go, holy cow. Secant squareds, tangent squareds, square roots with tangent squareds in it. So I go back to my tables, and the tables that we've looked at so far, let's get rid of that, have had no trigonometric stuff. There's no trigonometry in any of these. There's no trig functions anywhere. But there are trig functions here. Tables of trig forms. Sine squared of u, cosine squared u, tangent squared of u, looking through all of these. I don't see anything that looks very complicated. Here we've got some sine to the n cosine, sine cosines, nothing with tangents and secants. Here's something with secant, but no tangents in the formula. What else have I got to look at? So there's some more inverse trigonometric functions. None of those look anything like what I've got. And now we've got exponential and logarithmic forms. That's not going to apply. Hyperbolic forms, don't worry, you're not going to have any of those. Forms involving these other radicals with 2AU, nothing. So what do we do? Well, as I said before, the challenge is to make your integral look like one of the formulas. So clearly, we're going to have to do some playing around. So remember, u in these formulas is a function. And we need to see what could we do? Could we let one of these trig functions be equal to a u? Well, I let u be equal to the tangent of theta, because I have a tangent of theta in the numerator, tangent of x. Or I should have said tangent of x here. There are no thetas. Let u equal tangent of x. Sorry, got my thetas and my x's mixed up. So let u be equal to the tangent of x. What's the derivative of that? du is secant squared x. If I ignore this 9, just get rid of that 9, put it out in front, then what I have in the numerator here is I have a u squared times du. So in the numerator, I have a 9 times the integral of a u squared du when I let u be equal to the tangent of x. Du is secant of x. And then if I let a be equal to 5, in the denominator, I have an a squared minus, well, tangent squared is my u squared, minus u squared. So I have this form right here. 9, just forget about the 9, that's not important. I have the integral of a u squared du over the square root of an a squared minus u squared. Let's go see if that's in my trig tables. So going back to the beginning. All right, so we want an a squared minus u squared. So that could be in this first grouping here somewhere. And so I look down and I get to number 34. There she is, u squared du over the square root of an a squared minus u squared. The key is in our problem, u is equal to the tangent of x. Remember what I said? U is some function. It could be an exponential function, an algebraic function, a trigonometric function. It could be just x, but it's some function. And so all we need to do is take this formula back to our problem, which I have right here, plug in the a and the u, and then just multiply the whole thing by 9. And there you have it. You're done. So again, fitting the integrand, the integral, the problem, into one of those forms is key. Always ask yourself, all right, what could I let u be equal to? A's are easy. A's are just the constants, but you've got all these functions in here. How do you do that? And so that is the key to using the tables. I think the one that I just did, exercise 2, is one of the more difficult ones from the homework. So now you've got a head start on that. All right, so the next problems Desmos. I'm really not going to be doing anything with this because we've already done this before. In your set of notes, I forgot to actually make this a definite integral, so I added a 5 and 2 as bounds of integration there. I just kind of did that arbitrarily. But I've already talked about, so by this time we're into week, at least 7. You have been using Desmos extensively to evaluate your integrals to check your work as we've been going through this. So you know how to do that, and Desmos always gives you out a decimal number. So really there's nothing to talk about there or with this one here. These are the two problems that we just did. The difference here is here we have algebraic answers. We have answers algebraically, and with Desmos we're actually getting numerical answers. All right, that is it. This homework should be a fairly quick one. This is going to be this one video for this section. Just make sure that you know how to use the tables.